Hola, ¿qué tal? Muy buena.
Hello, good evening. Good evening to this. Welcome to this session. Is there life on Tuesday? Is there life in Mars? It's a play on words in Spanish, but it doesn't work in English. This is our logotype for tonight. So we have Christophe Galfard here. Look at what fantastic books I've got. You know that he got a doctorate in physics from Cambridge, and he worked with Stephen Hawkins, and so of course they worked on black holes. So this is what it says, and he says that he's still got the same jersey that he had when he started to investigate. Well, we'll have to ask him about that later on. So we'll be asking him lots of questions about what he's discovered over these years. So he was at, as we said, in Cambridge University doing a lot of research, and luckily for us, Christophe Galfard then devoted himself to disseminating all this knowledge, and we've got these fantastic books in our hands, The Universe in your hand, and also How to Understand E equals MC squared. So we'll be talking a little bit about this, life on Mars and life on Tuesday. So welcome to everyone who's come along for this session at Fundación Telefónica. We're delighted to have you here, and thanks to Blackie Books for bringing Christophe along. And we're going to have the opportunity also to be able to travel to the universe through Christophe's books, and but we've got him here in body, not just in mind, but in body too. So a big round of applause for Christophe Galfard. Thank you very much.
Muchas gracias. Perdón, mi español.
Thank you very much. My Spanish is terrible, so I can't speak in Spanish. I'm going to speak in English, okay?
I've been told that the audience here at Fundación Telefónica is extremely bright. Is that true? Yes. So I will consider that you all have some basic knowledge in quantum field theory, in quantum spacetimes. Yes? Good. And we can go from there, okay? So, first, let me ask you a question. Who has done physics in the room at some stage in their life? 1, 2, 3, yeah, a few. Good. So the others, you won't understand anything tonight, which is good. So let me tell you one thing. Why do we do physics? Why do we learn physics at school? So let me give you an example. I'm taking this bottle of water. I'll open it. Can you open it for me? Thank you. You shouldn't have done that. I'm going to throw it at you now. Okay? And I'm going to bet that the water will fly off up to here, then it will stop, turn around, and come back in my bottle. Who wants to bet? Usually the people in the back, they want to bet, not in the front. Why do we laugh? Why don't we think that the water can do that? Why? Because we all have the intuition that there are laws in nature and that these laws cannot be broken. The role, the aim of physics is to find these laws. And we've managed to do that. It's a miracle if you want. We did not know in the first place that we would be able to find some laws, but we did. And thanks to these laws, we understand where something will fall if I throw it. That's Newton. About 100 years ago, we went further. When you think of it, compared to the universe, we are extremely small. Compared to the quantum particles, we are huge. We kind of float in between two infinities, one immense, one very, very, very small. And what we see around us, what our intuition and our common sense is based on, is our senses, what we can detect around us. And I'm sure you will all agree with me that it would be extremely pretentious from our small body and 5 small senses to believe that we can have the intuition of everything. It would be pretentious, and actually it would be wrong. The laws of nature, when you go away from our senses, are not the same. They're not the ones we are used to. And what I'm going to talk to you about today is what we've discovered about our universe as a whole. We're going to make a little journey in outer space, all the way starting from Earth, all the way to the Big Bang. In the beginning, everything is going to be very easy. At the end, you won't understand anything anymore. Okay? Which is normal, because we can't use our intuition all the way through. But let's see. So, let's start with some images. We've all been on holiday or taken some time off at some stage at night to look at the stars. We've all seen a sky like that. Maybe not as beautiful as this one, but we've all seen this. I'm sure most of you know the name of the white streak that you can see in the sky. What's it called? Milky Way, yes. So what is it, the Milky Way? It so happens that today we know, but our ancestors, they did not. What is the Milky Way? Is there something behind? What is that? Well, every time you look at the stars at night, you only see a small portion of the night sky. You can't see all of it, because the Earth is round. Now imagine you could walk around the Earth with a camera and take a picture of the night sky every night, and you go around the Earth. When you come back, you patch all the pictures together, and you get this. On this image here, this is a composite of 37,000 pictures taken at night. This is the whole sky as you can see it from the Earth. And now you see that the Milky Way looks a bit flat. This is pictures, right? This is what we can see from the Earth. Now imagine we could fly up and have a look at it from above. Then you would see this. This is the Milky Way. It's a galaxy. It's made of 300 billion stars. Now, you may wonder where the Earth is. Some very optimistic people think that the Earth is here. Well, it's not. The Earth is somewhere around here, around the Sun, which is there. Now, to have an idea of the distances involved in such a picture, you may wonder. Imagine you are in the future, that humankind has colonized the whole of the galaxy, that you have friends living everywhere around planets that orbit other stars than the Sun. And you want to talk to them. How do? You take your mobile phone. You take your phone and you call them. So let's have a look. Not you again, you've done that before. I'll ask you, what's your name? Angel. You are on the moon, Angel, okay? I'm going to call you. When you talk to someone on a mobile phone, your voice is transformed into light, into electromagnetic radiation, meaning that your voice travels at the speed of light. To get to the moon, light takes 1 second. So I will ask you a question, and you wait for 1 second to answer, okay? Angel, can you see Madrid from the moon?
No.
Good. I have the answer 2 seconds later. That's about that. Now you, what's your name? Tanya. Tanya, I'm going to send you to the Sun, okay? Tanya, is it hot on the Sun? Oh, wait. Let's do it again. Tanya, is it hot on the Sun? Yeah. 3 seconds you waited? Yeah. Let's do the real thing. Okay, we'll have to wait 8.5 minutes. Okay? Tanya, is it hot on the Sun? Now you can pick a book and start reading, because I'll get the answer in about 17 minutes. And that's not very far. Now when you look at all the stars that you can see in the sky, obviously there are plenty, and obviously there is one which has to be closer to us than all the others. This one is called Proxima Centauri, and there happens to be a planet around it called Proxima b. Well, if I send any of you out there and give you a call, I'd have to wait about 4.5 years for my voice to reach you. So I'll have an answer in about 9 years. That's a long time to wait. Basically only your parents answer the phone, nobody else. And so 9 years to get the answer back, just to know where this is. The Sun is here, Proxima Centauri is here. You didn't see, I didn't move my finger. To reach the center of our galaxy, where there is a supermassive black hole, light would need to travel for more than 20,000 years to get there. So that you get a little feeling of distances in space thanks to that, okay? Now, we can't take a picture from outside like this because it's too far away. You'd have to send a satellite with a camera for hundreds of thousands of years, if not millions of years, to be far away enough to see a galaxy like this. But if you have imagination, and some physicists do, this is what the Milky Way would look like, for real, if we were to have a look at it from a side in the universe. And the Earth is somewhere around here, that far away from the center. And you probably all know that the Earth spins on its axis, north-south, it spins, that's day and night. And it so happens that the axis never moves. And it's something like this. And the Earth spins like that. North always points this way. So Spain being in the northern hemisphere, it means that the sky, as you see it from Spain, is this. Oh. No more battery. The thing is under there somewhere. If somebody can do that. I can do it without pictures. Thank you. Which means that the sky you see from Spain, as I said, is this part. If you've ever been to the southern hemisphere, then you'd notice that the sky is much brighter. Why? Because the stars you see is all this. The other thing that it means is that when you have a look at the night sky, well, the Milky Way is not just the white band. All the stars that we can see in the night sky are stars that belong to the Milky Way. All of them. Now, let's go back to the question we had before. Is there something beyond the Milky Way in space? Again, most of our ancestors, since the beginning of humankind, did not know the answer. They thought that was it. That's the whole universe. But we built telescopes. And with telescopes, we can see further than the eye. And when you use a telescope and zoom in, what do you see? You see there are other galaxies. This is a real picture. This is Andromeda Galaxy. Andromeda, if you have a friend or a lover on Andromeda, if you want to give him or her a call, you'd have to wait for about 4 million years for the answer to come back. So don't fall in love with someone on Andromeda. That's really tricky. So again, this is a real picture. Andromeda is 3 times more massive than the Milky Way. It has about 1,000 billion stars. The Milky Way, Andromeda, are the 2 biggest galaxies in a small group of about 40 galaxies called the local group. That's our neighborhood, our galactic neighborhood in outer space. Now, another thing you need to notice on a picture like that, you may have seen this picture before, is that there are loads of dots here. These are stars, but they belong to us, to the Milky Way. You can't tell them to move for the picture, so they are there. But there is a huge void between the last one and this galaxy that you see in the background. 2 million light years of nothing between Andromeda and the Milky Way. I have a few bad news for you tonight. Here comes one. You know that things are attracted to each other because of gravity in outer space, right? And so Andromeda and the Milky Way, they are attracted to each other through gravity. But they don't move fast enough. And when you don't move fast enough around one another in space, you fall towards one another. So we will someday collapse. Well, we will merge, let's say, with Andromeda. Andromeda will come and hit the Milky Way. Andromeda is 3 times bigger than us. So you get the result, right? If you want to know when that will happen, you have to ask that at the end. So let's see if we can see further than that. We have our telescopes, and let's zoom in the dark and see further away. This galaxy is 2 million light years away. Now let's have a look at another. This is the Cigar Galaxy. It's about 12 million light years away from us. Now, some of you may have seen many pictures of galaxies on the internet and everywhere, and this one is really not pretty compared to what you can see. So why on earth did I choose this one? Well, something special happened to that one. This is a picture from 5 or 6 years ago. Now I'm going to show you a picture that dates January 24, 2014. This was seen. You see under the little arrow, there is a dot which appeared right there. What's that? That's maybe a star that exploded. Why do we care? Well, there is a question you may have asked yourself. How do I know that this galaxy is 13 million light years away? If I want to check the distance between you and me, I can take a ruler, 1 meter long, and I do 1, 2, 3, you're 4 meters away from me. If I want to see something that's further still, I can use a laser, like this one. I know how fast the laser moves. If I put a mirror somewhere, I can send my laser and wait for it to come back to me, measure the time, and I know how far away it is. That's how we know the distance between the Earth and the Moon. The astronauts who went on the Moon left a mirror on its surface, and from Earth we send a laser and check the time, so that we know the distance between the Earth and the Moon up to a millimeter. The precision is up to a millimeter. It's really good. Now let's try with this one. I have my laser, I send it towards that galaxy and wait for it to bounce on some planet or something and come back. Well, for it to come back I would need to wait 26 million years. Not an option. So how do we do that? How do we know? Well, let's have a look at exploding stars. When a star explodes, when a star dies, at the end of its life, it looks something like this. Be careful, it's very violent. Boom. The blue that appears now behind is a real picture of a star that exploded. It's called nebula, the cloud that is left out there. And you can see there is a white dot in the middle. That's the heart of the star that is still left behind. And the rest is the nebula. This one is the cat's eye nebula. Nebulae, we know many of them. Here is another one. It's called the Helix Nebula. And again, there is a white dot at the center. It's called a white dwarf. On this one, can you guess the name of this one? Somebody? Butterfly. Thank you. Very good. I asked a bunch of French kids a few weeks ago what they thought this was, and they said, no, not a butterfly. It's two fish that kiss each other. The French, huh? This picture, it's this star here which exploded and left, and all the dust that you have here is the surface of the star that grows in space, bigger and bigger all the time. Now you may wonder what will happen to this dust. It will grow and get dimmer and less dense, and maybe get lost in space. Well, in space you have time. So if you wait 1 million or 10 million years, maybe another star will explode. And if another star explodes, you have more dust. And then another, and then another, and then another. And in the end you can get huge clouds like this one, which contains maybe the dust from 100 or 1,000 stars that exploded in the past. This nebula is called the Eagle Nebula. And if we look carefully, some special things happen in there. We can zoom in. All these are real pictures. There is no special effects whatsoever. Here we get closer to a nebula that is very special. It's called the Pillars of Creation. And again, something special happens inside. But what? Okay, question for you. Why are you not flying right now? Those who did physics, you don't say. Why are you not flying? You should have done physics, the other ones, huh? Or you may think that you all can fly, I don't know. So why can't we fly? Can't we fly like that? Gravity, yeah. Because there is the earth underneath our feet, dragging us down. Now imagine for a second that we are in a spaceship, far away from Earth, and the spaceship doesn't accelerate anymore. It's there, okay? You don't have gravity underneath your feet anymore. So you're floating on your seat. And if you wait long enough, hundreds of thousands of years maybe, then the gravity that will attract you is not that of the Earth, there is no Earth, it's the gravity of your neighbor, here. So if you do a very long trip in space, do choose who you're sitting next to, because it's very important. You get closer, closer, and if you wait long enough, you will form a ball floating in the middle, and there as well, just because of gravity, 3 balls like that. And you will start circling each other and collapse into a 1 ball. You're in the middle, that's the wrong seat. Everybody's going to crush you and you'll be extremely hot in the end. This is exactly what happens in these clouds. You have small dust, particles everywhere. At first they attract because of some strange force, and then they form bigger dust. And bigger dust attracts through gravity the dust next to it. It starts to form small rocks, pebbles, and then bigger rocks. They look like potato-shaped asteroids, and then bigger. There's so much dust, you can go on for a long time. And after a while, because of gravity, the thing gets round, and it becomes huge, and it becomes so big that the gravity crushes everything in the middle. So much so that you can reach temperatures that sometimes go up to 50 or 60 million degrees. When this happens, a star is born. That's exactly how stars are born in our universe. All these pink dots that you have here are newly born stars that came out of this cloud made out of the dust of stars that exploded. Now, if we could travel inside the cloud that you can see here, that's what you will see. That's what you would see. This is not a real film, right? We made that up. So you have a ring of dust that collapsed and created a star that's appearing in the middle. And if you look carefully, there is a small cloud here that will become a little ball that turns around the star. That's a planet. This is how we imagined planets and stars were born in space. This was pure theory until 2015, 2 years ago, when for the first time astronomers managed to take a picture of such a place in space. And there we go. Here's the picture they took. In the center, you get a blob, because there's a lot of dust still there, so everything shines. You can't really see the star, it's in the middle right there. But all the dark rings around, these are planets being formed right now. This is how the Sun, the Earth, and all the other planets were formed. Now, to just give you another idea of scales, we saw the scales of galaxies. Now let's have a look at the scales of planets. You probably know there are 8 planets around the Sun. 4 are big, 4 are small. The Earth is the biggest of the 4 small ones. If the Earth has this size, then just slightly smaller than the Earth you have Venus, then Mars, then Mercury. And then you get the giants, like Uranus, Neptune, Saturn, and Jupiter. Jupiter is the giant of giants. It looks big compared to the Earth, but compared to the Sun, it's not that big. If Jupiter has this size, then the Sun is about something like this. If you look extremely carefully now at Jupiter, it will disappear, and you will have the size of the Earth instead. That's home. And if you look even more carefully, I'll tell you stop. You have to watch this screen now, everybody. I'll get on the side. When I say stop, stop. That's Madrid. Here you can see. Now, why does the star shine and not the Earth? Why? This is a real film of the Sun. Why does it shine? Where does it take its energy from? Well, you may all know that matter, the matter we are made of, our skin, the air we breathe, the ground we walk on, is made of atoms. What's an atom? It's a nucleus with electrons around it. And if you look at the nucleus itself is made of small balls. They have names. We call them neutrons and protons, but whatever. There are small balls inside the nucleus. Well, if you look at all the atoms, you see that they're all made of the same tiny things inside. So you can classify them by size, from the smallest one to the bigger ones. And the two smallest atoms we know of in the universe are hydrogen and helium. They make up for 98% of the known matter in our universe. About the time of the Big Bang, they made up for 100% of the matter we know in the universe. So 2% changed. How did that happen? Well, it happened in stars. In stars, like everywhere else, you have mostly helium and hydrogen. And this thing crushes by enormous gravity whatever lies in the center. So you have to imagine the tiny atoms out in there being pushed from all sides. The atoms, they lose their electrons, you only have the nuclei left. And the nuclei, they crush until they have no choice but to fuse, to glue one to another. This is called a thermonuclear fusion reaction. And this reaction has a strange property. You need an immense amount of energy to start it, to get it started. The whole gravity of a star. But when it starts, it releases even more energy. And that energy has to go somewhere. So it fights its way out from the center outwards. And when it reaches the surface, it shines as light and some other particles. So basically a star is a factory that creates big atoms out of small ones. You get two small atoms, you glue them, you create a bigger atom. At the end of its life, when a star explodes, it ejects all the atoms it created in space. These form a new cloud that will form planets. All the matter that is in your body right now was created in a star that exploded a long time ago. Some of you may have gold with them on rings or something like that, or even a tooth or something. Gold is different. Gold is not created in stars like these. There's not enough energy to create gold. We've discovered for pretty much certain how gold is created in our universe a month ago. When those two, maybe some of you have heard that we've seen two neutron stars collide, emitting what they call gravitational waves. We saw them through gravitational waves, I may explain that later, and we saw them through light, and we saw that when they collide, they do create the gold that is now in your ring or in your jewelry. The gold we have was created in one of the most powerful explosions we know in the universe. Now let's go back to that. So a star, what it is, there is gravity that tries to make it smaller, like pushing everything towards the center. And there is this thermonuclear fusion reaction which tries to push everything outwards, like me. And you get an equilibrium. When you have an equilibrium, you get the sun. The sun is at an equilibrium. It doesn't change size. The gravity and the fusion, their energy, they match. We're very lucky for this to be the case. Well, actually, we are not lucky. If it was not the case, we wouldn't be here. It wouldn't be nice to be next to the sun. Now, second bad news of the night. Someday there won't be any more small atoms in the center of the sun. When that happens, gravity will take over. And when gravity takes over and there is nothing to prevent it, the sun will shrink. And when it shrinks, it will trigger new reactions, which this time will be much, much more powerful than gravity. And the sun will explode, leaving behind its heart, the white thing you saw before, the white dwarfs. So, because I know some of you may be scared about all this, I called my friends at Cambridge last week, knowing I was coming here, just to ask them again, I had made the calculations, but I wanted to be sure I wasn't wrong, to ask them again when the sun will explode. And they all came with the same answer: it's next Thursday. So if you have things to wrap up, do it fast. No, the real answer is about between 4, 5, 6 billion years. So we really have some time before this is going to happen. Still, there will be a white dwarf left behind. A white dwarf is the heart of a star that is left behind after the explosion. It is extremely massive. If one day you travel in space, let's say we have better technology in a month or so, and you travel in space, and you see a white dwarf next to a huge star, don't be mistaken. The master is the small one. Its gravity is much, much stronger than the one of the huge star. So much so that it will grab its surface and eat it. You will see some kind of river of plasma flowing from the big one to the small one, which would be feeding on the big star. And white dwarfs have a certain property. If you leave them alone, nothing happens to them. It may take 100 million years, but they cool down and nothing more happens to them. But when they eat a star, when they reach exactly 1.4 times the mass of the sun, they explode in one of the most energetic explosion we know. It has a name. It's called a type 1a supernova. These explosions always occur when a white dwarf reaches 1.4 times the mass of the sun. Again, who cares, right? Who cares? Well, let's see this. You're on holiday, you walk in the countryside, okay? It's a good, nice day, you walk, it's fine. Then you see a village. You go into the village. Nice village. There's a church. Nice church. You go inside the church. There is this bell at the top of the church, right? I said the top of the church because I can't remember what you call the clocher in English. Anyway, there is a bell up there. Nice bell. You walk up the stairs. You see the bell, you put your head inside the bell, and you ring the bell from inside. What happens then? You know the sound of the bell at its source. If a few hours later you're back in the countryside, assuming you're not deaf, you can walk to the countryside, listen to the church, to the bell, and if you compare the sound inside the bell to the one you receive, you can tell how far away you are from the bell. You can tell the distance. Well, that's exactly what type 1a supernova are good for. This picture here is a type 1a supernova. We know the light it emits at its source. We can check what light we receive here on Earth. By comparing the two, we can tell how far that galaxy is. And thanks to that, we know it is 13 million light years away. So let's continue. We know our universe is at least 13 million light years big in one direction. So if you draw a sphere, that's 26 million light years from one side to the other. We take our telescope and try to look further. What do we see? Another galaxy. This one is called the Sombrero Galaxy because it looks like a Mexican hat. So it's the sombrero. It's not a joke. It's its real name. This one is some 20-30 million light years away from us. Let's keep going. We have our telescopes. Let's use them. It's taxpayers' money after all. So let's look further. What can we see? Another galaxy. Well, this one is special for two reasons. One is that it looks very much like the Milky Way. It is about 250 million light years away. And the other thing that is funny is that earlier when I showed you Andromeda, all the dots that you could see around were stars. This is not the case anymore. Here, all the dots you can see are galaxies. You've zoomed so much that you don't even see the stars around us anymore. This is a really tiny part of the sky. The only stars here are the ones which are crossed. There's some here as well. These are the stars. All the others are galaxies. There are a lot of galaxies in our universe. Now I'm going to show a short film about 30 seconds long, in which you will travel through the 400,000 closest galaxies to us in space. They are the real ones. They are at the right place and they have the right shape. This really is a 3D map of our cosmic neighborhood. And maybe we can dim the lights for that. I'm not going to talk because if you really were in space, there's no sound in space. Every single dot in this image, in this little film, is a galaxy. Every single dot contains hundreds of billions of stars. The whole Milky Way, our galaxy, is just one of all these dots. If you have a friend that you think is a bit too pretentious, just show him or her this film. The furthest galaxy in this film is about 1 billion light year away from us. Now, let's reflect for a second on what it means to be 1 billion light year away from us. You may have heard that the stars that we see in the sky are dead. Who has heard something like that before? A few people, yeah. And now it's just to check who is depressed. Who thinks that all the stars we see in the sky are dead? Good, they're not. Very good. So, what does it mean to see a star and it's dead? Imagine that you have a grandmother in Australia, and she writes, she takes a selfie of herself. She's not very good with technology, so instead of sending it as a text message, she prints it and sends it as a postcard. So you have to wait. Let's say 3 weeks later, you get the postcard at home with the picture of your grandmother. No one imagines that his or her grandmother looks like the picture right now. That's how she looked like 3 weeks ago. As far as you know, she may be dead by now. In the meantime, right? She's not, don't worry, she's not. What it means is that when you get a postcard like that, with a delay, you are seeing a picture that comes from the past of your grandmother. Because she is now, and you see her as she was 3 weeks ago. It's exactly the same in space. When a star shines, it sends in outer space an image of itself. The image will travel for a while, and then we are here on Earth and we receive the image. When you see it, you see the star as it was when it sent an image of itself. That's why if you look at a star that is 1 light year away, you see the star as it was 1 year ago. When you look at the sun, don't look at the sun. But if you could look at the sun with the naked eye, you would see the sun as it was 8 minutes ago. If the sun dies now, we will know about it in 8 minutes, not before. There's no reason it will die in 8 minutes again. But yeah, Proxima Centauri, if it explodes or whatever happens there, we will know it in 4 years. If you look at Andromeda, you see Andromeda as it was 2 million years ago. When you look at the furthest galaxy here, you see the galaxy as it was 1 billion years ago. That means you have a glimpse at one specific place of what the universe looked like 1 billion years ago. You're kind of walking through the past of our universe. You can see what's happening. Can we look beyond this 1 billion years? Well, this is another picture, real picture. This is one of the furthest picture we have of the universe. The furthest galaxy in here is about 13 billion light years away from us, meaning it looks like it looked like 13 billion years ago. Now we have our telescope, so let's keep going. Let's zoom in and look beyond that galaxy. What do we see? Two possibilities. Either the cameraman who took the picture that day forgot to take away the black lid at the back of the camera, or we don't see anything. We actually don't see anything. We see a wall, all black. No more stars, no more galaxies, no more nothing. Who knew there was an end to our universe? A wall like that. You did? Good. You did as well? You're not sure? Yeah, he kind of did, yeah. Who felt it, if you prefer. There is, yeah, an end to our visible universe. It is a very, very strange concept. So I told you that the beginning of the talk was going to be easy, and I told you that at some stage you won't understand anything anymore. That stage starts now. Okay? So, we see this. Nothing. Let's try to understand what it means. Okay? Now, special effect, we go back to the previous picture. When we look at a picture like that, we can analyze it. We can try and see what it means. When you're in the street and there's a car driving by you, it does something like that. The sound of the car doesn't really change. It's because it's moving that the sound changes. When the car comes towards you, it's higher pitch. When it moves away from you, it's lower pitch. That's called the Doppler effect. Well, in space, that effect exists as well, but not with sound, with light. When something moves towards you, it looks more blue. When something moves away from you, it looks more red. That is called a redshift. That's the name. And physicists about 100 years ago, looking at pictures like this one, it's not like this one, but like this one, they realized that the further the galaxies are, the faster away they're moving from us. Meaning that if you go far enough, all the galaxies in the universe are moving away from us. Now think about that for a moment. Imagine, picture yourself, you, in the middle. You look around you, and you see everybody moving away from you. You will think there is something special with you, obviously. So, we're in space, we see everything move away from us. What's the logical conclusion? We are at the center of the universe. It's kind of obvious, right? You're here, you see everything move away, but you're at the center. Well, that's not the conclusion that the scientists got to. What they thought is that actually the galaxies, they are not moving at all. So why do they look like they're moving? Not because they're moving, but because the distance between us and them stretches. The distance gets bigger. The galaxies don't move, it's the distance that stretches. Now if you look at the universe like this for a second, then you might think that everybody's moving away from you, but so would you. So would everyone. Everybody would move away from everybody else. There's no center anymore, or everybody's at the center of the universe, whichever you prefer. They're both equivalent. That's what we call the expansion of the universe. The expansion is not that the universe has a limit, and that it eats on what? Nobody knows. It's not that. The expansion is the distance inside our universe, within our universe, in between faraway galaxies stretches. The distances stretch. That's the expansion of the universe. Now, once we have that, let me give you an example of why scientists are so intelligent. You ready? You have to concentrate, okay? Everybody's ready? Good. They thought that the distance is stretched. They can see it in the sky. All the scientists got together about 100 years ago and start to think about what this might mean. They got together, they got colloquiums, conferences, talks, dinners, and suddenly one guy came up and said, I have an idea. And the idea is the following, and the reasoning is the following. He thought that if everything moves away from everything else, then in the past, things were closer. Right, huh? We laugh because it's easy. So easy that Einstein himself refused to believe that. Why? Because it changed 2, 3, 4, depending on the culture, 1,000 years of beliefs. Since forever, as far as I know at least, the universe, what is the universe? The universe is some kind of space that is out there, a box if you want, with a clock outside, a divine clock if you want, that goes for everybody, that is outside, and things can move inside the universe. This is different. This says that the universe itself can change. This universe that was thought to be the same since forever suddenly could change. And if it could change, it suddenly meant that it could have a history itself. Not the things inside the universe, but the universe itself. And if it can have a history, then it maybe has a beginning. And this is such a deep concept that, as I said, Einstein himself refused to believe that at first. Then he agreed with it, but at first he refused. Such a simple, very simple argument was refuted by the brightest brains of the time because it was in contradiction with all the beliefs we had before. But now let's not take that for granted. Let's see what happens if this is correct. Let's say this expansion and universe has a history thing is correct. Let's see what we can deduce from that. Let's have a picture in our mind. You have all the galaxies that you see. We know about 1,000 billion galaxies in our universe. All of them made of hundreds of billions of stars, with many planets around each star. Picture all that in your mind, if you can. Then imagine that the distances get smaller. All this energy that is everywhere gets packed into a smaller and smaller volume. Then, at some stage, a long time ago, there must be so much energy that even light should not be able to travel. If you try to get some light through a wall, you can't, there is too much energy. But it works for radio waves. But imagine something that's so thick that no light, no electromagnetic wave whatsoever can go through. That's a universe that is opaque, not transparent to light. Wherever you are, you see nothing. It's too dense. And then you go smaller and smaller and smaller and you hit something very strange. But let's not get there so quickly. Now if you turn around that story and start from the beginning, the universe is very small, it gets bigger, it's so dense, there is no light, you can't see anything, but it gets bigger, so everything gets diluted, and one day, suddenly, it should become diluted enough to become transparent. Once it's transparent, light can go. When did that happen? Maybe we can look in the sky. We should, if that is true, see in the back of everything the wall that corresponds to when our universe became transparent. And there you go. This is a picture of the wall. Now some of you may think he's joking, he just took a black picture from his computer and is trying to make us believe that's the wall of the end of the universe. Well, you're right, it is a black picture from my computer. A very nice one. And so, did you notice that there should be something wrong here? When the universe became transparent, a second before, or even less than that, it was not transparent. Meaning it was extremely dense, meaning it had an enormous energy, meaning it should have been extremely hot. We can actually calculate how hot it should have been. And it's about 3,000 degrees. 3,000 degrees? But that emits light that our eyes can see. 3,000 degrees, you can see it with your eyes. And it's very bright. So this should be blindingly bright. The night sky should be brighter than the sun. So there is something wrong. Well, unless the universe kept expanding. If it kept expanding, the temperature went down, cooler and cooler. And we can actually calculate how cool it should be today if everything I've told you before is correct. And if you calculate that, you get something that's around minus 270 degrees Celsius. That's not a light you can see with your eye. You need a special tool for that. You need special detectors. And we built such detectors after that minus 270 degrees was predicted. And what we found this. This time is a real picture. This is a real picture of the wall I was talking to you about. All the dots here correspond to temperatures. Dark ones and white ones are separated by 0,00001 degrees. So, meaning that it's all pretty uniform temperature. And what temperature is that? Minus 270 something degrees Celsius. As predicted. This was not known before, and we saw that in the sky. This is one of the best smoking gun we have, that our universe began very small. Now, you may think, okay, but when did this happen? 13.8 billion years ago. That we can see in the sky. Good. How long happened before that? Well, we can't use telescopes anymore to look beyond, because we can't use light. Light doesn't go through. It's a wall. So we need to use different things. We need to use theory, and we need to find out what the laws of physics were when the universe was extremely hot. That's exactly what we do in particle accelerators. With particle accelerators, we manage to smash particles one into the other to reach temperatures at the collision that can go as high as 100 million billion degrees. Meaning that we know the physics of the universe up to that temperature. Meaning that we can go back very, very far beyond that and make an estimate of what happened beyond. From this, we estimate that this happened 280,000 years after something very special happened. What's that very special thing? Well, that's the whole universe. Make it shrink, because it goes, when you go back in time, it gets smaller and smaller. At some stage, it will be so shrunk, there will be so much energy that none of the theories we have today apply anymore. The two theories we have are quantum physics for the very small and general relativity for the very big. That's gravity. Those two theories are very humble. They tell us when we cannot use them anymore, when they break down. And we can tell that both these theories break down some 280,000 years before that. That 280,000 years before that is what we call the Big Bang. Not because really something happened, or maybe, but because the theories we have break down. Actually, something very strange happened anyway, as far as we understand it today. For example, gravity is a theory of space and time. When gravity breaks down, space and time break down. The very notions we have of space and time don't apply anymore. At all. We can't use them. So we can say that the Big Bang that lies behind that thing is the birth of space and time as we know it, as we know them. So yeah, beyond that, we can't use the telescopes. We need new tools. Maybe the gravitational waves that we've discovered, we now can detect, will be able to go through and show us what's behind that, because gravity waves, they walk through everything. They don't care about obstacles, they just shoot through. We don't have the tools to see those gravitational waves yet, but I'm sure we will someday. In any cases, to conclude what I've told you up to now, there is one thing that's important to remember. Everything I've told you, we haven't been there. We haven't been to faraway galaxies. We haven't been to the end of the visible universe. We've understood that from here, from the Earth, thanks to one thing, our brains. We're the only species we know of on Earth who has ever been able to do that. And just for that, I think we can be very, very proud of ourselves as a species, all of us. Thank you very much for listening. Thank you.
Muchas gracias.
Oh, thank you so much. That was so fantastic. So you take a seat, Christophe. I'm going to bring the books over, and I'll just tell you that we've got a fantastic bookshop at the door so that you can all get your books before you leave. And after our fantastic presentation, are you okay? Is everybody comfortable? Christophe, are you comfortable? Oh, I hope this table is not going to fall. Okay, anyway, so you can get Christophe to sign your books afterwards. Thank you so much for taking us on this journey. So while you were traveling to the university, you offered us this travel. Our illustrator Enrique Flores was listening to everything. He's been watching everything. He's been drawing everything that he saw on the screen. So let's see what Enrique has drawn. He's not just drawn you, he's telling the story also of what you were telling. So I'll remind you that we have a microphone here, and you can ask questions. You're the Martians or the Tuesday group, and I'd be delighted if you also ask lots of questions. And also we can look at the questions on our mobile phones. Because there are so many people out there studying all these things who want to ask questions. So I wanted to ask you a question, Christophe. There's a word that you mentioned several times, which was imagination. And you think it's so funny that a physicist should use the word imagination, but at this moment when our senses don't really explain things, a physicist needs something more, right? He needs imagination.
What do we do when you try to do science? You try to picture a situation where, one, you cannot go, two, your senses don't work, three, you have no clue whether it's correct or not. The only tool you have is imagination. That's the only one. The scientists who discovered most of the things I talk about in the books, or that I told you right now in these talks, the scientists that came up with these discoveries, they're the most imaginative people I know. The only ones that could compete are artists, in a way. It's not so different. In both cases, you try to translate a feeling or an idea you have about reality using the tools you have. An artist will use painting, writing, drawing, sculpting, whatever, filming. Scientist uses mathematics. That's their tools, and without imagination, you're not going to go anywhere.
Supongo que ese es uno de los motivos por...
So I think this must have been one of the reasons why Einstein was so fascinated with this, because it wasn't a question of pure reasoning.
Well, it is a question of pure reasoning, but we're humans. We have feelings. Well, most of us, and when something is shocking, there is this saying in science that for real new revolutionary ideas to spread through the scientific community, you need to wait for the old scientists to die. This is the idea that every step you go one step. It's extremely hard to get out of the culture you had in the first place. It's extremely hard to agree suddenly that the universe may have a history. It may be in conflict with thousands of things that you had learned before, and yet in front of overwhelming evidence you have to say, yeah, who am I to know? Nature is there. We have to be humble and say, oh, okay, it's like that. So it's really not easy to go beyond what one thought in the beginning. And that applies to Einstein as well.
En tus charlas y en tus
In your books, in your talks, you've demonstrated that physicists can excite imagination and excite an audience and readers, and also make us want to know more things about the universe. But it's very difficult to be able to explain to people who don't know anything about physics what it's all about, what you know. So what is the most difficult thing for a disseminator, for a physicist, to be able to explain to people? What's the most difficult thing?
The most difficult thing?
Si hay pequeñas cosas difíciles.
There are small things, it's useful too.
Now, to begin with, I think one of the most difficult things for non-scientists to understand is the scientific method. Because science, that doesn't mean truth. And lots of people are sometimes uneasy with the idea that science kind of has a truth and you disagree with it. Science is not about truth. Science is about trying to find the best approximation to the laws of nature. It's never perfect, it's never exact, and you always have to doubt it. But that doesn't mean that when a new discovery is made, what was there before was wrong. The idea of something that is wrong is very precise in physics. The idea of what is true doesn't exist. We can only know what is wrong, and something that is not wrong. That doesn't mean it's true. So that's the first part. And the second thing is the previous question, to show that science is actually a dream. It's about imagination. It's about being able to travel wherever you want in your mind, in places where no one has been before, in places, there are so many mysteries around us. It's crazy. The more we learn, the more we are familiar with what is around us, the bigger the faraway mysteries become. And yeah, I mean the joy of searching for these things is absolutely overwhelming. There's no children here, right? So I can quote Stephen Hawking, who said once that to find something that no one has found before is a bit like sex, but it lasts a lot longer.
Bien.
Okay.
I think that is in our I won't say genes, I don't know, culture or whatever, that makes us happy when we discover, when we understand, and unhappy when we don't understand, etc. And there is this notion that science is actually, you are going to have most people relate to science as they related to it when they were kids at school. But that's not the same at all. We don't care how good you were at school. It's not because you were good or bad at school that you can't be curious. And it's this curiosity that I think is difficult to get through and share.
Bueno, yo creo que ha alimentado.
I think you've really fed our curiosity there a great deal. So this is one of the very positive things. But also, it's one of the tough things about science also. The more you learn, the more questions we have, right? And the more doubts we have also. So today we have a doubt. Well, why haven't you talked to us about black holes? Yeah.
Come on.
Shall I start a new talk right now? It's ready. It's my computer. No, okay. So I can say one thing about black holes. They are fascinating because they look like beasts and monsters and stuff like that. But there is another reason. I said before that we have two theories that explain pretty much everything we know in our universe. One theory that explains the very small, which was called quantum physics, and the other, the very big, gravity. It's Einstein's theory of general relativity. Now, these two theories are the best ones we've ever had. They're not perfect, we know that. We know that if we go to two extreme energies, they don't work anymore. But if you stay in normal places, they work perfectly. We've never had theories that work so perfectly. But there is a problem. They disagree with each other. For instance, the notions of space and time are not the same in quantum physics and in Einstein's gravity. They're not the same. Space and time in quantum physics are the same as Newton. And Einstein's gravity told us that that's not at all the case. Space and time are very, very weird concepts, much more difficult than what Newton thought. And so that's fine. Once for the small, once for the big, different notions, no problem. But as I said before, the Big Bang is when the whole universe that we can see, the whole visible universe, was so small that it entered the quantum realm. Meaning that they do have to come together. Quantum physics and gravity both have to talk to each other at the Big Bang. Now, the holy grail of science today, of theoretical physics, is to find a theory that merges quantum physics and gravity. We don't have that. We have candidates like string theory, loop quantum gravity, and stuff like that. Good luck to translate that. And we have theories like that which try. We don't know which one is correct. We don't even know whether we have the correct one. But the problem with the Big Bang is that there's just one Big Bang, and it's in the past, and we can't even access it. Now, there's another place where the big becomes small. Black holes. Black holes occur when huge stars die, not the ones I've shown you before on the pictures, much bigger ones. When that happens, their heart collapses on itself, and that creates a black hole. As you have a huge amount of matter that becomes smaller and smaller and smaller and smaller. The big becomes small. So black holes do need quantum gravity effects as well. That's one of the reasons why they're cool.
Mientras que buscamos ese santo.
While we're looking for this holy grail in quantum physics and relativity, we can do a sort of a marriage and combine the two, perhaps. So Christophe Galfard has explained to us the theory of MC squared, etc. E equals MC squared. But perhaps we could do an interview as if it was like the beginning of a dictionary to be able to understand. Richard Feynman said, if the universe is a chess game, these are the rules. And this is something we can understand. So can you tell us something about this book?
D equals MC squared?
Yeah.
Okay. E is the fifth letter of the alphabet. Equals means, well, you know. And M is the first letter of mother. Now, E is for energy. I'm sure most of you know that equation. E is for energy, M is for mass, and C is the speed of light. So this equation gives you an exchange rate, like if you went from euros to dollars, when you want to change energy into mass or mass into energy. This equation tells us that energy and mass are two aspects of the same thing. What that thing is, I don't know, but it's two aspects of the same thing. It means that if you have a lot of energy, you can create a tiny amount of mass. And if you have some mass, you can turn it into energy. And yeah, when you have some mass, the energy you have to multiply by c squared. C is the speed of light. That's 300 million meters per second. When you square that, how much does it get? Come on. Someone? A lot, right? It gives you a huge number. That means that with a tiny amount of mass, you can get a huge amount of energy. This is what this equation means. But it actually is something more. If you remember at the beginning of the talk, I told you that we are tiny compared to the universe, and huge compared to the very small, so that our senses are not adapted to discover what the laws are in the very big and in the very small. But there is another region of reality we've never experienced either, and that's the very fast. You may think you run fast, you don't. You may think you go fast in a plane, you don't. You may think a rocket gets you to go very fast, that's not true. You never go fast. We humans never go fast. When we talk fast, we talk something that goes around the speed of light. And this equation tells us that the closer you go to the speed of light, again, the rules of nature change. Space and time, as we thought them since Newton, don't behave the same way anymore. And E equals mc squared tells you that you're entering in a new realm of reality. It is, again, pretty nice. Well done, Albert. Yeah.
Sí, que dices que le podían haber dado.
You said that perhaps he should have got 10 Nobel Prizes, not one, and he would have deserved them, wouldn't he? Yeah. So I remember that you can pass me the questions with using the hashtag Vida Martes. You can do your questions on Twitter. So you say that this is an urgent question, that somebody's saying, good heavens, God, please ask him, why is the expansion of the universe going faster and faster? What's going to happen? Can you tell us? Respite.
Like, calmly. So, before we discovered what you've just talked about, which I'll repeat in a second, there were, since we knew about the expansion of the universe, basically two possibilities for our future emerged. When you imagine something that grows bigger, you have to think what can slow that expansion down. There is only one force we know of in the universe that has a very long-range effect, and that's gravity. And gravity is always attractive. Always. If I get closer to you, the gravity will get stronger. If I get closer to the Earth, the gravity will get stronger as well. It's always attractive. So gravity may slow the expansion down, and actually it does, right? So the question is there enough energy or gravity in our space to completely stop the expansion and get the reverse? So the two possibilities are, one, there's not enough energy, not enough gravity, and the expansion goes on forever. And then you get very cold because everything gets farther and farther apart. Or the other way around, there's a lot of gravity and the expansion slows down and hop goes the other way around and you get a big crunch where everything collapses again. And then in the first case you die of cold, in this case you die of heat. So pick your preferred one. The thing is, in 1990, and that was what the futures were. It's not going to get better. These are still the two possibilities. But in 1998, three astronomers called Rees, Sol, and Perlmutter, they discovered something strange. They saw that instead of slowing down, the expansion actually accelerates. Things go further apart faster, as if there was some anti-gravity thing around. Gravity, as I said, would drag me towards you, and this force repels. And it's on large scales, stronger than gravity. What is that strange force that repels, that anti-gravity force? No one has a clue. It's called dark energy. And in science, when you say dark or black or something like that, like black hole, dark energy, dark matter, when you have that in front of the name, that means we don't understand at all what it means. Nothing at all. So dark energy, we don't have a clue what it could be. But it seems to be there. Maybe it means our theories are wrong, but maybe it's actually there. And that dark energy is enormous. It consists of about 75% of the total energy of our universe. You may think, oh, that's okay, we know 25% of the rest. No. Dark matter makes up 21%. We don't know what dark matter is. And everything I've told you, everything you've ever known about and been taught about at school corresponds to the 4% that are left. The rest is mystery. Today, 96% of the energy of your universe is mystery, or not there. We don't know, but there is a mystery. Anyway, to finish your question, I'm looking at the camera out there. As of today, it doesn't seem that the big crunch is going to happen, because there is this dark energy pushing things aside, apart from each other. It seems that we're more going towards very cold death. I like to say that with a smile.
Bueno, creo que es el momento de...
Okay, I think while you continue to ask us some questions, and we still can keep expanding and this light is spreading everywhere, I think it's the moment perhaps to give the floor to our Martians or Tuesday goers. Have we got the microphone out there? This is like antimatter for me, this microphone. Where is it? For many years you've been looking for practical applications of the theory of relativity until it's been discovered, this application that it has in synchronizing GPSs across the world. So you explain gravitational orbits. I think, will this have an impact, this theoretical application in the future? What do you think these applications in the future will be?
Do you mean that with the theories, what kind of technologies will emerge in a few years? Is that your question? Okay, there is a basic rule with this thing. It's very simple. It's that usually when a scientist makes a prediction about the future, it's wrong, right? It never works. So actually, I have absolutely no clue what will happen in the future. But if we're allowed to dream a little bit, our understanding of space and time may allow one day for interstellar travel to get to some of the other planets. Now, as of today, for instance, if you want to travel from the Earth to Proxima b, that planet I told you about before that was about 4 light years away from us, if you use the best rocket we today have, the fastest one, you need to be a bit patient to get there, because it would take you around 200,000 years to travel to that planet. But we know that if we go fast enough, if we reach speeds that are close to the speed of light, which we can't do, but if we do, our time would not flow as fast as it does on Earth. Meaning that your time would be kind of very slow compared to someone on Earth. Meaning that, and the distances would shrink as well. If you don't understand what I'm saying right now, that's normal. The distances when you go fast, they shrink. If right now I walk 1 meter like this, if I do exactly the same 1 meter but shooting by at 99.9996 or whatever is the speed of light, this 1 meter would look like a millimeter for me. The distance is, and you will look like very tiny spaghettis that I fly by. And time on my clock would not tick the same way. So we know that theoretically it's possible, if you go fast enough, to cross immense distances in outer space in a lifetime. It's actually known that if you travel at the speed of light, your time wouldn't tick at all. Everything would be instantaneous. You could start now. I transform you into light. You fly for 12 billion years in space, get back in your body on the other side. For you, 0 second would have passed. You'd be exactly the same. The only problem is we have no clue how to do that. And I'm not sure we will be able to do that someday. So no, it's very hard to predict what could be done. One of the things that is very probably more will probably have more impact on our society is everything that comes from the quantum world. If we talk about decades in the future, we may have quantum computers and things like that, and that's going to change a lot of things because, for instance, none of your bank accounts will be safe anymore, and some other stuff like that. Don't be too scared.
Okay.
We'll find ways around that.
Well, let's play a little bit trick, because Christophe has shown us that we can see the light of the stars of thousands of years ago, hundreds of thousands of years ago. But what about this strong, the eye of the telescope that Enrique can show us? This was just a few minutes ago. Let's see, how are your drawings going, Enrique? While we are looking at Enrique's pictures. Let's see. Come on, microphone, it's got to move there. It's good moving. After listening to you talk about the immensity of the universe and these stratospheric figures that you've mentioned, it seems to me impossible that human beings on Earth could be the only life form in this whole universe. Seems impossible. So could you talk to us a little bit about the possibility of other life forms in the universe? Thank you.
But let's see who believes in this room that there is alien life somewhere in our universe. Who doesn't believe there is alien life anywhere in your universe? Who believes there is alien life in this room right now? A few. So far, as of today, we are on the only known planet to harbor life. So, how can we probe the rest of the universe? In the question I just asked all of you, I said believe. Because it's a belief. We don't have any proof of anything so far. So what we would like to have is a way to maybe detect something somewhere else. But even that, how do you do? How do you check if there is life somewhere out there? The first thing is you need another planet. Well, 25 years ago, we didn't know if there were planets around other stars in our universe. Dozens of scientists were burnt alive in the past centuries because they just suggested there might be other planets out there. They were burned for that. Actually, they were right. The first planet to have been found around another star was in 1994 by Kelos and Taylor, two Swiss astronomers. As of today, we know of about, confirmed, I think it's about 3,400, maybe even more. There are tens of thousands of potential planets, and the estimate is that there actually are about, on average, 3 planets per star. Meaning that there are 1,000 billion planets in our own galaxy. Now, why is there only life on Earth? Is it just because we haven't detected other life from anywhere else as of yet? Well, maybe. We haven't had the tools for very long. We are not, as of today, able to look at the ground of another planet. The first real detector to be able to tell us something about atmospheres on other planets will be launched next year. It's called the James Webb Telescope. And this is the first time we will actually have a very good tool to detect what's in an atmosphere somewhere. We're not even talking about looking at the ground. We're talking about knowing what's in the atmosphere. Why? Because we want to see if, for instance, there is oxygen. on Earth, if you erase all life, oxygen will be gone, because oxygen doesn't stay very long here on its own. You need life to create it. So if there is a lot of oxygen, maybe there is life. And yet we discovered oxygen on a meteorite last year. We said, but maybe that's not, maybe there are sources of oxygen we didn't know of. It's very tricky. But there is one thing that we know. We can look at the life we know on Earth. And on Earth, every single living organism is made of the same stuff. And everything, and when I'm saying every single living organism, I'm not talking about men and women, right? I'm not talking about humans and chimps. I'm talking about humans, chimps, mushrooms, bacteria, any kind of microbial life, anything. Any life form you might find works along the same principle as us. And it needs one thing for sure: liquid water. So when we look for life somewhere else, we look for a place that may harbor liquid water. And that's much harder to find, or not. There may be liquid water everywhere. We kind of know for sure, let's say, that there are oceans of liquid water on moons of Saturn and Jupiter. So maybe there are aliens there. We know for sure that there was a long time ago an ocean on the surface of Mars. So maybe there are still pockets of water under the ground. Maybe there are bacteria there as well, or stuff. We don't know. But what I do believe is that since we're starting to get that technology, we should begin to have very nice answers in the decades to come. I would be so happy if we were the first generation of humans to actually find life somewhere else. I'm pretty ready to bet that we will.
Una pregunta que ha mandado alguien.
A question sent by somebody on Twitter from Sebastian. Detecting gravitational waves. What would be one of the main beliefs that would change if we detected these? What main belief would change?
What main belief would change? Or has changed, because we did detect them. So the first answer is absolutely none. Zero. Why? Because gravitational waves were predicted in 1916, pretty much immediately after Einstein came up with his equations about gravity. Not E equals mc squared, it's another equation. And they were indirectly known to exist since the 1970s. There was a Nobel Prize in 1983, I think, for having proved that they actually exist. So we've known that for a while. The thing that changed recently is that we managed to build a detector to look at them directly. And that for me is exactly the same revolution in tools, not necessarily immediately in thoughts, but in tools. That it's the same revolution as when Galileo invented his telescope in the first place. Because since the beginning of mankind, what tool did we have to look at the universe? One, light, sight. That's the only thing we had. Galileo gave us a tool that allowed us to see more light. And then James Maxwell, a Scottish genius, told us that the light we see is just a small part of a much wider range of electromagnetic waves like X-rays, UV light, infrareds, things our eyes can't see. We built detectors. All this came from the telescope of Galileo and the discovery of what light is. And so we could look at the universe through the whole spectrum of electromagnetic waves, light, let's say. This is something different. It is not light. It is gravitational wave. It's something different, a wave that moves in space and time and gets through you right now. There are passing through you right now, gravitational waves. Can you feel them? No? You'll get used to that. this is a new tool. The first thing Galileo saw with this telescope was that the moon had craters, so it's not a perfect sphere, and that there were some kind of moons around Jupiter, moons that were orbiting Jupiter, not the Earth, and that there were comets that could cross things in space. Previous to that, many people thought that the whole heavens was made of crystal spheres centered on the Earth. The first sphere was the Earth, then there was the moon, then the sphere of the moving things, then the sphere of the faraway stars, and that everything was moving like that. Seeing a comet go through that collapsed the idea that there were spheres holding stuff out there. Seeing moons around Jupiter meant that the Earth could not be the center of the universe anymore. The first thing we saw, well, scientists saw using gravitational waves, is that they saw black holes colliding, merging. We had no clue. We thought that might happen, but we had never seen that. And that gave us a hint as of how the supermassive black holes that exist at the center of our galaxies were formed by small black holes merging. Or not, maybe it's too small. The two black holes we saw merging were 29 and 36 mass times the mass of the Sun, respectively. The one at the center of our galaxy is 2 million times the mass of the Sun. There are so many answers these things may give us in the long run. So yeah, to go back to Galileo, the first thing he saw was the craters on the moon, and that the moons of Jupiter were circling Jupiter. This is the first thing we saw with black holes colliding with gravitational waves. Then Galileo's telescope was improved, and we saw the other lights I told you about, UV, etc., which allowed us to see different stuff in our universe. We do not know what the next generation of gravitational wave detectors will allow us to see. Maybe they will allow us to see beyond that wall at the end of the visible universe, and back maybe to the very first instance of our universe. We do not know yet.
Ojalá.
Oh, that'd be great if we did know. Okay, so let's see who's got the microphone now. Andrea? Yes, my question is, we know that stars are born after the death of others, and that matter is not destroyed, but it converts. So what happened with the Big Bang? Something had to start it. So what happened for so much energy to suddenly explode?
That's the... If you start from the theories we have, as I said before, if you go back in time, you reach a place where you can't use those theories anymore. So you need other theories. And these theories need different concepts for space and time and all the things like that. So there's a big question mark there. How did that happen? In 1983 or 1984, for the first time in human history, some people gave an answer to that question. Not necessarily the right one, but a mathematical one. And the two people who wrote the article are James Hartle from Santa Barbara University and Stephen Hawking from Cambridge University. And they built a mathematical model in which you could, I'll use technical terms, right? But in which you could, thanks to some kind of quantum fluctuations, create a universe out of nothing. I'm not saying it's the answer, but it was the first one, and it opened up the possibility of thinking mathematically the birth of our universe. Now, since 1983 or 4, I don't remember, others have come up with other ideas about the birth of our universe. For instance, there are some scenarios or scenarii in which our universe was created by the collision of two other universes who unfortunately disappeared but created ours. That's one. It's called the kpyrotic universe. It probably doesn't work, but it's an idea. There is another one which says that you have bubbles within bubbles within bubbles of universes that are bubbling all the time, and from an infinite past to an infinite future. Maybe. We do not know. We don't have the answer to that, and we haven't been far enough in these theories to be able to conduct an experiment or give a prediction that an experiment could tell is right or wrong. We don't have that yet. So for now, it's pure imagination, and that's for me the most fun part of research.
Edna.
Okay, another question. Currently, we at school on first and second year and learn about theories, and we get explanations which are in force, have been in force for many, many years, and some even have been shown to be incorrect. But the theories of relativity and quantum physics, they continue up to university level and continue to be valid. So what do you think that we should still be taught these theories that have been should we learn them in a historical sequence, or should we be learning the ones that are most correct today, most accurate, considered most accurate today?
¿Está el ministro de Educación aquí esta noche? La idea de que una teoría está equivocada es un poquito, digamos, tiene un doble filo. Sabemos que la teoría de Newton, para mí, es perfecta. ¿Por qué? Porque sabemos cómo funciona, funciona donde funciona, sabemos dónde no funciona y sabemos por qué, porque sabemos qué pasa después. Esto es perfecto. Entonces, debemos seguir estudiando la física de Newton, porque todo lo que tenemos a nuestro alrededor es física de Newton. Si queremos volar un avión, si queremos caminar, si queremos conducir un coche, si queremos hacer cualquier cosa, todo es física de Newton. Es un genio que básicamente explicó, bueno, no explicó, sino que describió con unas cuantas ecuaciones prácticamente todo lo que puede pasar a nuestro alrededor, y esto es algo perfecto a la hora de empezar a aprender física. Entonces, si queremos ir al siguiente paso, un paso es cuando la gravedad es demasiado fuerte, que ya no funciona la ley de Newton. Pero esto no significa que la teoría esté equivocada, significa que no se aplica, o que es demasiado o que, digamos, las condiciones no son las adecuadas. Luego tenemos que pasar a Einstein. Einstein funciona, la teoría de Einstein funciona, pero si vamos de una gravedad muy grande a una gravedad...
So Newton is part of Einstein. It's not wrong. It's just a special case when gravity is small. For quantum physics, on the other hand, we do not yet know. We know on paper, but now on paper also, we know how to get from quantum physics to Newtonian physics as well. But we don't really understand the physics of the transition from one to the other, and there's still a big interrogation mark, a mystery, how to get from the very small to Newton. So no, I don't think we should bypass Newton, because basically that's what you were saying. I think it's important. No, I know it's not what you were saying, but I think that's what you meant without knowing it. The Newton is important, but do we need to teach kids about quantum physics and general relativity? I think in a way, yes. Why? Not through the equations, but just through the dream. Let me give you an example. When a kid watches something he or she likes on TV, let's say, to use a simple example, football. When you look at a football player on television, you can project yourself into what you would become if you were a football player. You can see the end results. You're on TV, you have big muscles, you run fast, you can do stuff. You don't necessarily have a real idea about how much work you need to give to get there, but you see what you would maybe be able to do. In science, we don't have that. You only see the work. You don't see the extraordinary dream that you can reach if you go all the way through. And I think that kind of dream is something that we should teach kids, to give some glimpses every now and then of how joyful it would be to do that. So yeah, does that answer your question? No. A little bit.
Bueno, yo creo que Edna tiene esta...
I think that you have this dream in your brain, but perhaps you can. Would you like to be a physicist or study something that has to do with this area? It seems to me that you still want to say something else to Christophe. Is that right? Come on, make the most of it. You've got your chance now. Does somebody else want to ask a question? And another of the Martians, Fernando? Okay, so having explained everything so marvelously, all the theories, and to everyone here, now that we're getting closer to this very cold, icy death, I have to ask a question about understanding the world as physicists do, and how big becomes small, and small, big, time, space, etc. How can you experiment? How can you experience feelings towards what you see and what we call timidly people, or compact matter, whatever? How do you feel about humans after all this?
I'm not sure I understand.
Fernando es adorable, de verdad, ¿eh?
Fernando is adorable, yeah.
Fernando's lovely, really.
Es desde la más sincera admiración.
I say this from my total admiration of people. Do people change in your view? When you know all these things, is this what I'm just trying to explain what you're asking? What do physicists think about feelings? Oh, is that what you want to ask? Okay, what do physicists feel about feelings?
I'm having a conversation with the interpreter. It's very nice. So we came to an agreement that your end question is, how do scientists feel about feelings? Is that pretty much what you wanted to ask? Okay, we have an equation for feelings, which now. Maybe a way to enter your question is, can science and mathematical physics explain everything? Maybe, but we're not there yet. Meaning that there's no way I could put some mathematical equation behind a feeling. I may think somewhere deep inside me that it is biological, or chemistry and stuff like that, but we have no clue how to describe that, and it is so complex that as of now, you may as well consider it pure magic. That's for one. Now, it is possible that you will one day walk into a scientific lab and you will discover that scientists have no feelings at all. But I think that's wrong. That's not true. There are people like everybody else. How do scientists feel about feelings? I'm trying to think at the same time an intelligent answer to that question, but most scientists are humans like the others. Okay? I'd put it this way. So, yeah, it was said sometimes that Einstein saw in people wavelengths, but I doubt that's true. I think you can tell the difference between a pure wavelength and a human. Although, actually, there aren't any, but you can't see that. Anyway, I don't know.
Bien.
I like humans. Yeah.
Bueno, precisamente.
So, because you like humans, we all like humans, we're all going to have the opportunity of getting Christophe to sign our books. So, before we get up, can we ask this for Enrique Flores for his summary? Please show us, Enrique, what you've drawn of the Milky Way or your impressions, whatever. Is this black matter?
Más o menos.
More or less.
Mira la Vía Láctea. Milky Way.
There we are, the Milky Way. It's fantastic. Thank you so much. Thank you, Enrique, for having drawn these pictures. If you learn all this off by heart, you're going to pass all your exams in physics and at school, you people. So thank you so much for being with us, and thank you for inviting us on this trip and having written these fantastic books, which you can get in the vestibule and the hallway. So you don't miss the opportunity of getting Christophe to sign your book. So please buy them for yourselves, buy them for your family, and because everyone will learn, they'll have a great time. They're fantastic books, really, so all your family and your friends can get so much out of it. So thank you so much, Christophe. Thank you, and thanks to everyone else. Thank you.